All right, I think so. We're live now. So once again, welcome everyone to the Frontiers talk. Thank you for joining us. So today's program is that we have Hannah McAleese from Belfast joining us, but I'll introduce a bit more about her in a bit. Just want to have a quick series of advertisements for you to be aware of. There's a series of lectures on foundations of quantum mechanics being held by Florian Marquardt, and they're all online and highly well rated. And so if you're interested in brushing up or learning again, we highly recommend you go to these lectures, and there's a link that you can see. In addition to that, just a quick revision of our house rules, of course. Be respectful. Please, can you switch off your mics and your videos? And if you have questions, please ask them at the end of the talk. You can type them in the live chat if you're joining us through YouTube, or as always through Zoom, you have the capacity to ask directly as well by simply raising your hand. I hope also that everyone is aware of our research seminars page, and you can download a calendar to be aware of all the upcoming talks. And finally, the next talk will be on the 18th of November by Montessori. So without further ado, let me introduce our speaker today. Hannah, who's joining us from Queen's University, is a PhD student at Professor Mauro Petronos's group in the Quantum Technology group. Her PhD focuses on non-classicality in media-scale quantum systems, and includes looking at entanglement and quantum discord. And so today she's going to be talking about, I guess, a main topic of her PhD. So without further ado, Hannah, I want to pass it over to you. Let me just stop sharing.
Okay. Yep, so hopefully this will come across fine, and yeah, please let me know if you can still see everything. That's okay, yeah?
Yeah, it's wonderful. Over to you.
Okay, so thank you very much for the invitation for me to do the seminar. It's been a really great series so far, and yeah, very privileged to be a part of it. So the topic that I'm looking at today is on macroscopic quantumness, and looking at, so I'll talk about this more as we go along, but how we can kind of tailor the macroscopic quantumness with optical measurements in optomechanical systems. So I'm just going to start off by giving a little bit of background and motivation, and then introduce the system that I'm looking at, the measure of macroscopic quantumness that I'm using as well. And the real aim of my project is to analyze the role of measurements in generating macroscopic quantumness in a mechanical state. So we first look at Homodyne measurements, and then Heterodyne measurements, and then I'll add a bit about what happens whenever you add noise in this as well. So yeah, just to start off, macroscopic quantumness is obviously very highly linked to Schrödinger's cat and Schrödinger's thought paradox from 1935. And yeah, so we know that we can have quantum superpositions of microscopic systems and atoms, and how does that translate into our kind of macroscopic classical worlds? And there's so many open questions about the nature of that and how that all works, and where is this line between things that can sort of behave in this quantum mechanical way and things that can't. So one thing that I'm just going to introduce now, although I'm sure many of you are familiar with it already, is the Schrödinger Cat State. So this is a superposition of two coherent states. And we're just going to look at the Wigner function here, which is just, which I've shown in the slide. So you have two distinct Gaussians, which represent the two distinct coherent states with kind of opposite amplitudes. And then you have the interference pattern in the middle, which shows that it is a quantum state. This negativity in the Wigner function shows that you're in a non-classical state. And so to study this topic of macroscopic quantumness, many have turned to cavity optomechanics for this, because you get the chance there, as you see in the diagram, you have light interacting with a mechanical mode, sort of transferring momentum to it and causing it to oscillate. And through sort of manipulating the light mode of the cavity, you can create these non-classical states of the mechanical mode, which is often you're able to have a system here where the mechanical mode is visible to the naked eye. And so really what I'm building on is the kind of seminal Bose-Jacobs-Knight paper from 1997, where they kind of started off theoretically preparing these non-classical states in cavities with a moving mirror, and then also looking at the paper in the New Journal of Physics from 2013 by Lee, also kind of with a similar concept, but kind of building on that and exploring that a little bit more. So we're kind of further expanding on this in this work too. So we have a measure of macroscopic quantumness that we will be applying to this system. And this was proposed by Lee and Zhang in 2011. So macroscopic quantumness is quite a complex and sometimes controversial concept, because there isn't just one clear definition of it. There's not really only one aspect that you can really attribute to macroscopically quantum systems, and there's not just one way of quantifying it. There's several have been proposed, and they're all sort of have their different aspects that they're considering for macroscopic quantumness, and also maybe looking at specific systems or specific states. But so we have chosen this one by Lee and Zhang, and I've shown it here. So this is a phase space based measure, and it's really looking at kind of the Wigner function of these states. And so we have this bit that I've underlined in blue here, and it's looking at the magnitude of the interference fringes in the Wigner function. And this is related to quantum coherence, sort of related to the non-classicality of the states. And then you've also got this part that I've underlined in yellow, and it's the characteristic function of the state, which measures the frequency of the interference fringes. And this measures the size of the system. So in this way, you're kind of quantifying at the same time the quantum coherence, the quantumness of the state, and the size of the state. So just some more properties of it. It's actually, as much as this is focusing more on the kind of non-classicality side of macroscopic quantumness, it is also measured to, it's also related to a measure of robustness against decoherence. And that's the rate of purity decay, which I've shown. And so it does kind of confirm it as a measure of macroscopic quantumness, because it isn't only measuring the kind of one aspect of non-classicality, but it's also branching into the aspect of robustness, which other quantifiers focus more on. And then you've got this upper limit as well, which is the number operator of the, well, for us, what we're going to be looking at is the mechanical mode. So then you've kind of got a good gauge of like how large the macroscopic quantumness can be in the system as opposed to what it actually is. And you can sort of gauge a little bit more through that. And just one really great advantage of this measure is that it's straightforward to compute. So it just makes it a lot easier whenever you're dealing with these kind of Wigner functions and characteristic functions, that you can plug them in, and it's quite easy to use as a measure. So the actual optomechanical system that we're looking at here, I've written the Hamiltonian at the top. So it's this kind of straightforward interaction between the number operator of the optical mode. So the A is the annihilation operator of the optical mode, B is the annihilation operator of the mechanical mode. And the interaction here is between the number operator of the optical mode and the position of the mechanical mode. So then whenever we find the time evolution operator of this, we get this, so two rotation terms and also a Kerr-like term, which suggests that the optical mode is going to be in a non-classical state. And then also this conditional displacement operator, again, just kind of relaying that the state of the optical mode and the state of the mechanical mode are going to be correlated. And this is what we find when we look at the time evolved state. So Cn is just the kind of coefficients, which I've just summarized in this one Cn term, because it does get quite messy. So then you get that the cavity or the optical mode is in a Fock state, and the mirror or mechanical mode is in a coherent state, but the coherent state actually depends on the Fock state that the cavity is in. So you can see that the two are entangled. So this is the system that we're working with, and the aim for us is to generate a superposition of mechanical coherent states. So at the moment we've got this convex sum of coherent states, and we want to be able to sort of narrow that down to kind of a clearer superposition between maybe 2 or 3 coherent states. And the way to do this is by using Homodyne and Heterodyne measurements. Okay, so so what we do effectively, I mean, this is a purely theoretical project. So just talking about this from sort of a modeling aspect. So you can model this by projecting the cavity field onto a suitable Gaussian state. So Homodyne detection is projecting the cavity field onto an eigenstate of the quadrature just x theta. So it would be the position quadrature if theta is equal to 0, and the momentum quadrature if theta is equal to pi over 2. And then this is what the actual eigenstate of the quadrature looks like at the bottom, where h is a Hermite polynomial. And the resultant state of the mechanical mode looks like this. So the n at the front is just a normalization term. And again, you've got these parts that rely on the measurement settings, so x and theta, as well as the kind of initial part of the state and the coupling in the state as well. So whereas Heterodyne is projecting the cavity field onto a coherent state, which I've labeled sigma. And again, in the yellow box, this is the resultant state after a Heterodyne measurement. And we find, yeah, just sort of see where this sigma comes in and how it affects the state. So I'm going to start off by looking at Homodyne measurements. First of all, just kind of look at the coupling strength, K. So I labeled this in the Hamiltonian as G, and then this sort of change it into a dimensionless parameter. So K is G divided by the frequency of the mechanical mode. So this is the coupling strength that we're looking at. And yeah, what we really want to see is how these kind of measurement settings, x and theta, affect the macroscopic quantumness of the state. So we're going to look at that. We're going to look at the Wigner functions, just to compare it with that Schrödinger Cat State that we saw at the start, and how the features change. And we're also going to look at the fidelity with the Schrödinger Cat State as well. And then at the end of this, we should be able to make some statements about the optimal measurement strategy. So first of all, looking at the coupling strength. So we've just chosen x equal to 0 for now, and just sort of had a few different values for theta. So we can see that the macroscopic quantumness rises as k increases, and also approaches its upper limit of the number operator of the mechanical mode. So we do see that we need large coupling strength. Now this is a drawback because obviously large coupling strengths are difficult to achieve. And well, I mean, at the moment they have not been achieved experimentally in terms of, k being equal to 1, for example, which is kind of what we'll use a lot in this project. But there is progress being made, and we're hoping that once experimentalists have reached that goal, that this will be something that they can really put into practice then, and this will be something that we'll propose going forward. So just looking a bit closer then, just fixing k equal to 1, and looking at x and theta. So we've kind of got a few different values for theta along the bottom, and just seeing it as x grows at the top. So then we can see that there's this dip in this plot of the macroscopic quantumness. So as x grows, you see that the macroscopic quantumness grows, but also as x grows, you see that there is a detrimental effect that theta, non-zero theta, has on the macroscopic quantumness. So we find that the best strategy to start off with is to project just onto an eigenstate of the position quadrature to keep theta as at 0, and this will increase the macroscopic quantumness. So in terms of looking at a suitable value for x, we find, again, just sort of looking at this more closely, we find that there is a value whenever we look at the upper limit of the macroscopic quantumness. There's a value where the macroscopic quantumness meets its upper limit for theta equal to 0, and then for the other thetas, which we're going to look at just out of interest, but knowing that these aren't going to be quite as good as the theta equals 0 case, they don't quite meet it, but they do get very close. And it's at this point sort of x equal to 1.427. So this is what we look at going forward, is this kind of interesting point where the macroscopic quantumness meets its upper limit. So looking at the Wigner function then, we do see that it is similar to a Schrödinger Cat State. It has similar features, the two distinct Gaussians, the interference in the middle, the negativity. So that's for the theta equal to 0 case. Then whenever we look at the other two cases, we do see that there is kind of this detrimental effect. The state becomes both kind of more lopsided, so not sort of two kind of easily, I don't know, like two distinct Gaussians, but one is kind of large and the other sort of diminishes, so that it sort of becomes more just like one Gaussian state. And then also the interference patterns are still there, and then negativity is still there, but they do get smaller. So then, just out of curiosity, looking at the fidelity with a cat state then, and the fidelities are quite disappointing, which is strange because you can see the features in the Wigner function. So we decided to look into this a little bit more, and investigate why the fidelity was so low whenever all of the features are there. So I've just a simplified state of the state after homodyne detection. So we've got these coherent states which depend on n, the Fock state that the cavity field is in. And so we look at the coefficients of the state as n grows, and we find that there's really only 3 that we need to take into consideration. So we decided to simplify the state down a bit to just looking at these 3 contributions, and neglecting all the rest. And additionally, we added this parameter mu to the one in the middle because it stood out a lot from the other 2. And then decided to see what the effect was of the fidelity whenever we played around with this parameter mu. So mu, as it increases, the fidelity lowers. So we're able to kind of narrow that down then and say that the fidelity with a cat state is lower because of this contribution, this part of the state. And otherwise you can get very high fidelities with a cat state. So just a summary of results for this part, for the homodyne part. So we know that we need a strong coupling strength K, and that the best strategy is to project onto position eigenstates. And the macroscopic quantumness grows as X grows, as this kind of amplitude grows. But we sort of honed in on this one value where it reaches its upper limit, and at that point we can find non-classical cat-like states at that point. So then focusing on heterodyne measurements, we're just going to start off again by looking at the coupling strength K, and then this coherent state amplitude sigma of the coherent state that we project onto the cavity field. Again, just looking at the macroscopic quantumness and the Wigner function, but comparing it to the Homodyne results as we go along and see kind of which one is better. So again, we have the similar graph for the heterodyne states, and we see first of all that the green, so the solid lines correspond to the macroscopic quantumness, and the dotted lines correspond to the upper limit. And we see that the red and the blue and the green are very, very similar. So we see that the macroscopic quantumness is actually, it doesn't matter too much what the real and imaginary parts of the coherent state amplitude are. It's more the absolute value of the coherent state which has the bigger impact. And then just comparing these, the two plots, the heterodyne measurement plot and the Homodyne, so we see that we get quite similar results for whenever the coherent state amplitude it just has the kind of imaginary part just equal to I, and whenever we have this x equal to 0, theta equal to 0 part, so this kind of the red line in the Homodyne case. But whenever we look closer at the two, we see that in the heterodyne case, the macroscopic quantumness is closer to its upper limit for smaller values of K, and therefore you can argue that there is an advantage to heterodyne over Homodyne here. So just again to have a closer look at the Wigner functions. So we see that again. We have the interference, we've got the negativity, but it's maybe not quite as cat-like as the Homodyne ones that we've just seen were. And so this actually changes with the coherent state amplitude. So for smaller coherent state amplitudes, we find that whenever we look at the different contributions of the different coefficients, as we did for the Homodyne case, I'll just go back to that just to sort of make this clearer. So here we have these kind of three standout coefficients that we need to take into so it's really just more like one Gaussian state that you're taking into account, so which is why there's really kind of that only one Gaussian for this first kind of top left Wigner function that we're looking at here. But then it becomes more like the one that we've seen previously with the three different coefficients as the absolute value of the coherent state amplitude increases. So then we get something more similar to what we had before. And this is kind of also why the macroscopic quantumness increases in this case. So just a kind of quick summary of the heterodyne results then as well. So again, we need strong coupling strength. Again, we just sort of kept it after the initial thought, we just kept it at K equal to 1, looking at the different Wigner states there. Larger coherent state amplitude leads to larger macroscopic quantumness, and heterodyne measurements show advantage over Homodyne measurements. Finally, then, I just wanted to look at the effect of optical noise. So if we have this master equation looking at kappa as the decoherence parameter for the system. You know, what is the effect of this? What if photons can leak out of the cavity? And really what we used to evaluate this was the quantum unraveling approach that was put forward by Dalibard, Kasten, and Molmer at the start of the 90s. So basically, it's a way of solving the master equation where you split the time evolution up into very small parts, and so normally it just evolves in a quite natural way with a very, very kind of slight dissipative term. But every now and again, a photon can leak from the cavity. And then if you do this several times and you average over them, then it simulates the results of this master equation. So this is what we use to evaluate this. And the results here are pretty much what you would expect, that macroscopic quantumness decreases whenever you add optical noise, and the larger the noise, the more detrimentally affects. And again, it just gets further and further away from its upper limit, which is again unsurprising. And then again, looking at the Wigner functions, so you start off, so this, by the way, this is looking at the state of the mirror after Homodyne measurements. So it's kind of similar to the first set of Wigner functions that we saw. So with this kind of slight noise, slight dissipation in the cavity, we see that nothing much has changed. Still 2 Gaussians, still the negativity, still the interference. And then it kind of just morphs slowly into kind of less sort of 2 distinct Gaussians and kind of just sort of one joined Gaussian almost, that sort of curls round whenever you get to the bottom right one. However, it is still important to note that there is still a decent amount of negativity. It doesn't just dry up. The non-classicality doesn't vanish that quickly with dissipation. So there's still hope that, obviously, in an experimental setting where you would have cavity dissipation, that doesn't necessarily mean that the non-classicality would vanish straight away. So I'll just wrap up here. Again, just going over the sort of overall message. So strong coupling is needed between the optical and mechanical modes. For Homodyne, we need sort of a large, so like large amplitude of the eigenstate, and yeah, so again, the larger it is, the greater the macroscopic conditionalness will be, but then we kind of, again, focused on the x equal to 1.427, and that gave us some really nice results, some really nice Wigner functions. And then that it would just be the position eigenstate that we're projecting the cavity field onto as well. And then for heterodyne, we want a large coherent state that we are projecting onto the cavity field at that point. And we see the heterodyne measurements show an advantage over homodyne, and we see that noise has a detrimental effect on the macroscopic quantumness as well. So that's all I wanted to share with you today. Thank you very much for listening, and yeah, do you have any questions?
Thank you, Hannah, for that very excellent talk and introduction to your work. Before we start questions, should we? Can I ask everyone to unmute and just thank Hannah for that talk with a virtual clap, please? Yeah, so open the floor to any questions if anyone has.
I have a question, if that's okay.
Yeah.
Turn off my video. Hi, thank you so much for the talk. I just also want to relay that we had a YouTube comment from James Millen who says, thank you, Hannah, for the talk. I just had a really quick question about I think it was one of the first plots you showed, which was the non-classicality as a function of the optomechanical coupling. And there was like a tiny dip. So I think, maybe a few slides ahead.
Mm-hmm.
Ah, yeah, that one. So for the measure of non-classicality, there was this dip, or maybe a tiny plateau just before 0.5. And I was wondering if you know why this one is there, because I would have expected it to essentially just grow quite monotonically with the non-classicality or with the coupling increase.
Mm-hmm. Yeah, I'm not actually. Yeah, I'm not sure. This is something
Interesting.
that yes, I'll have to think about this, because you're right. It would seem like it should just kind of grow very naturally with it. So yeah, there must be some point where the coupling strength.
Yeah. I did just notice that it is a log plot. So maybe my intuition is just not, but it seems to slightly to decrease though. That's really interesting. So maybe something cool is happening there.
Yeah, no, I'll look into that. Thanks for that.
No worries.
I hadn't thought about that.
Yeah, sure.
Thank you, Sophia. So there's also a question on YouTube from, I'm assuming it's Jack Clark, but I'll be safe. It's Jay Clark. So the question is, so first of all, he's saying thank you for a very interesting talk, Hannah. And the question is, when computing the fidelity with the cat state, do you take into account the means of the states? I.e., do you compute the fidelity with a displaced cat state with a mean equal to your state?
So whenever I'm computing the fidelity, so I kind of, so I maximize over all of the different kind of cat states that you can have. I don't think I did displace the cat states.
Okay.
Yeah.
Okay, no, I guess that answers it. It's difficult to have a back and forth with a live YouTube chat, so. But okay, see if he has a follow-on question, then I can pass that on to you. Are there any other questions from anyone else? All right, so I have a question. It's just a clarification, I guess, for me to try to understand. So you talk about how macroscopic sort of quantumness becomes better when you project it onto the position quadrature in your measurement. Can you just go back to this? I didn't quite understand that point. Why does it become better?
Oh yes, sorry. Yeah, it's just because
I think it's this part.
There's this dip in
the
macroscopic quantumness. So yeah, there's quite a lot going on in this plot. So I probably did go over that quite quickly. There's so it's whenever you've got whenever x is high, then you have whenever you get away from the sides, which is x equal to 0 or x equal to 2 pi, which is
I think Hannah, you've cut off there your internet.
Quadrature, then you just have this detrimental effect. So it's just that you have less macroscopic quantumness. Okay. Yeah, is there?
Yeah, so I guess I'm trying to understand. So here, x is your position measurement that's carried out, right?
Yes.
And theta is the phase of the local oscillator in your Homodyne projection.
It's so theta. Yeah, it's the kind of the quadrature sort of measurement. Yeah. So yes.
Which is like, yeah, okay. So that's given by the local oscillator. Okay, I see. And so you scan through that, and so it's saying it's the dip, the minimum essentially occurs at pi. Is that right?
Yeah.
Or around there.
Just around. Yes. Yeah. Around there. Yeah. I'm not sure if it's exactly pi.
Yeah. Okay.
I think it is. I think it is actually exactly pi because it's sort of sine u sort of.
Yeah.
Yeah.
Okay. Okay. I think I sort of follow. Okay, that's great. Thank you. Are there any further questions?
I just have one additional really quick question. I was wondering if you have looked at any other measurement strategies apart from Homodyne and Heterodyne?
So we did actually, so just because I didn't have time for it in the talk, we did look at photon subtraction as well. But then that's kind of a bit of a changed system then. You're kind of not looking at exactly the same Hamiltonian or the same sort of final state. So yeah, you could get sort of very interesting non-classical states there too, but maybe not just kind of in this kind of nice Schrödinger cat clear similarities with the features and everything. And yeah, no, that was basically it. The main two that we looked at were Homodyne and Heterodyne, just because those are the ones that are going to give you the kind of superposition of coherent states of the mechanical mode.
Oh yeah, yeah, that makes sense. Okay, thank you.
Okay. So just a final call, I guess. Let me just have a quick check if there's any further questions on the YouTube live chat. No, but just Jack is just feeding back saying thank you for your answer, Hannah. All right. If there aren't any further questions, we should wrap up and thank you. Thanks our speaker, Hannah, once again. And we can do that by unmuting and just a final clap. I guess that's fair. That's great. Thank you, Hannah, and thank you everyone for joining us. So the next talk will be, as I said, the 18th of November, and you'll get an email circular for that soon. But once again, thank you and have a great day. Bye.
Thank you very much for having me.
Hannah, if you just stay behind once everyone's left.